Hi, everyone. Welcome to this webinar. So happy that you're joining me bright and early. For me, I'm in San Francisco. Wherever you are, thanks for coming. Today, I'm going to be talking a little bit about adjusting Kubernetes configurations for cost and performance. Before I get started, I have to show this one slide for legal purposes. Please don't sue New Relic, safe harbor, et cetera, et cetera. Before we get started, let me just tell you a little bit about me. I'm a principal developer advocate here at New Relic. I love talking about observability and love talking about Kubernetes. I love talking about some of the difficulties that can come with running cloud native workloads. But other than that, outside of work, I am a foodie and I love spicy food, especially hot pot. I think I'm getting some tonight, so I'm very excited. And yeah, thanks so much for joining me today as we dive into some of the complexities that come with running Kubernetes and specifically the costs that come alongside it. So let's talk first about what it means to run workloads on Kubernetes. So containers are really cool, right? Because you can basically take any programming language and any framework and shove it inside of a container so it can run in the cloud. So that means that you can run very, very interesting legacy systems in the cloud just by putting it inside of a container where it packages up all of the dependencies and things it needs to run and just shove it in the cloud. So that's why you can see like Azure and AWS support Cobalt microservices, which is wild to me. But what happens when you have multiple containers, like hundreds, even thousands of containers that you're trying to run in the cloud? That's where Kubernetes steps in. So Kubernetes is an open source way that you can automate operational tasks of managing containers, which includes a bunch of built-in commands for deploying applications, rolling out changes to your applications, scaling your applications up and down when you have more demand or less demand, and basically monitor all of your applications and makes it easier for you to manage the application you have running in the cloud. So Kubernetes seems like a great idea, right? It's a orchestration layer that helps you manage your containers at scale. But what are some of the downsides or the difficulties of adopting Kubernetes at scale? So it can make it really easy to overspend in the cloud. And let me tell you a couple of reasons why. So Kubernetes adoption enables decentralized deployments. So when we see teams move onto Kubernetes or fully embrace Kubernetes, oftentimes the way that they make decisions about deploying things or shipping things is very decentralized. So each team is responsible for shipping their own set of features, which is great in terms of empowering your developers to do more things and increase shipping velocity. But that means that it's very difficult to have a centralized way that all of your teams are deploying things and make it harder to monitor how much resources they're using for their applications and whether it's truly the most efficient way of going about things. So it makes it difficult because there's more moving pieces. And like I talked about right before, Kubernetes adoption enables faster release cycles. This is generally a good thing, right? As you can ship more features faster and you can be more agile in the way you develop software. However, this can lead to more moving parts to monitor. If you are constantly releasing new features, how do we make sure that the way you're deploying and creating these applications in the cloud is the most efficient that it could be built? How do we make sure that there's not excess waste being created in the cloud? The third thing I think is the most interesting is infrastructure as code, or being able to define infrastructure elements through things like a YAML file makes it really easy for developers to spin up anything they want with a couple of lines of code. So developers can spin up hundreds of GPUs in any region in the world from any major cloud provider today with like 2 lines of code. And this is great if you want to spin things up really, really quickly, but mistakes or oversights can be very, very expensive. Imagine a developer provisioning multiple EC2 instances that are XL or larger, and then just forgetting about them. That will be hundreds, if not thousands of dollars per day. And if that isn't caught, you're going to be footing the bill for that. So mistakes become a lot more costly when things are so easy to spin up. So what can we do to maximize our ROI on our cloud spend? So the first thing we can do is reduce spend and increase performance, so we can get the most out of deploying our applications to the cloud. So let's first talk about how we reduce spend. So when we talk about the overall cost of deploying things into the cloud, I like to look at this equation where we multiply the resource usage of the particular things we're paying for times the price of the resource. And when we talk about the price of the resource, these are basically controlled by AWS, GCP, Azure, all of the cloud providers. And it's kind of hard to kind of reduce that aspect of it. So let's look at what we can actually control as developers or operations people, which is the resource usage. And I can further split that resource usage up into smaller parameters. So I can define resource usage as the time of the particular object in the cloud being provisioned times by the quantity of the resource. So how do we make sure that what we're actually paying for is getting used to the fullest ability without as little waste as possible? So that's kind of what we're trying to do here. So that's where we introduce something called right sizing. How do we make sure that the workloads that we provision in the cloud is just enough for what we need, so we can avoid excess spending, or we provision enough where your applications are performing as expected, so we're not throttling or doing anything that will reduce performance. So here are a couple examples of things that can happen with Kubernetes and things in the cloud. So let's say, for example, my Kubernetes cluster doesn't give enough resources to a particular node and a particular pod within the node. So what could happen? So if a particular node with a couple of pods inside of it doesn't have enough resources, pods could be stuck as pending, pods could get evicted, and all of the resources, could be not enough for it to be run properly. So all of the performance and the particular pods could die or run out of CPU and memory, so your applications would just slow down to a halt, which is not very good. However, if you have too many resources allocated, on the surface level, you probably wouldn't see any red flags, right? Because all of your applications are running normally. However, your cost to operate the particular application will be really high. And if you are in a large enough team, you'll probably have a FinOps team, and they will find it and kind of ping you to make sure that you can reduce the amount of usage that you're spending on a particular resource, because there's way too many things allocated to this particular node. So a lot of organizations like New Relic have developed systems where they can tell if there's like slack cost or if things are not being used to its fullest ability. And then that is a really effective way to, for example, rein in a lot of excess spending, to have a team that watches over all of the things that your other development teams do and how they provision things in the cloud. So here's a couple scenarios of folks that could cause too many or too little resources to be allocated to the cloud. So the first scenario is to make up for bad code. So let's say, for example, I have an application that isn't the most efficiently written, where it can still do the job, but it requires significantly more resources to do the particular job. So instead of a developer going in and analyzing that particular piece of code to improve it, what they could do instead is just spin up multiple replicas of the inefficient code, therefore taking up way more resources than needed to make the application work. This is a simple example of what could happen for a developer to take up way more resources than needed in the cloud with their application. The second scenario is an accidental configuration change. Because you can spin up and build mountains with YAML files, a simple error in like a number that you define for a particular memory allocation can lead to huge changes happening in your environment. So you can have an accidental configuration change where a developer accidentally allocates 100% of available CPU for a particular pod, which means that no other pod could be scheduled in that particular node. So a particular accidental configuration change can definitely affect your entire application and environment to grind your entire environment to a halt, because no other pods can be scheduled in the same node. So yeah, that's another scenario. The third scenario, I think it's the most exciting yet terrifying scenario, is for escaped containers and cryptojackers. So there have been multiple instances in the news where hackers have gotten control over customers' AWS EKS or other Kubernetes clusters and installed malicious code like cryptojackers and other things that take up many resources that are not being used for your business purpose. So in this case, you can see there have been instances where engineers haven't detected the presence of a cryptojacker or a piece of code that mines Bitcoin for months because they don't have proper monitoring in place to figure out if all of their resources are being allocated and being used efficiently. So this is another scenario that could be jacking up your bill without you not even knowing about it. And this is one of the more malicious ones. So how can we prevent over-provisioning or under-provisioning? What are some of the guide rails that we can put in place to stop this from happening? So we can right-size our workloads with requests and limits within Kubernetes. So in Kubernetes, everything is a trade-off. So if you want to make sure that you have optimal performance and reliability, even during large spikes, and you want to guarantee that 100%, you're going to have to spend a lot of money on it because you want to over provision to make sure that even if there's a giant spike in usage, your application is going to be fine. However, that's probably not realistic for a corporation trying to make money. So it's always going to be a trade-off on cost versus performance and reliability. And the toggles we use to control all of those variables is requests and limits, which basically allocate resources for particular objects in your Kubernetes environment. So let's talk a little bit more about it. So on the left is a typical pod spec YAML file. And each container in the pod can set its own request and limit. So let's first talk about requests. So here you can see in the highlighted red box that I've set my memory and CPU request for 300 megabytes and 500 millicores. So the container is guaranteed. So container number 2 is guaranteed to get this much memory and CPU when it's placed into a node. So request is basically where you're saying, hey, this is the amount of resources I need for this particular container to run. And within the particular request, you can specify CPU resources. So CPU resources are defined in millicores. So if your container needs 2 full cores to run, you'd put the value 2000 millicores. If your container only needs a fourth of a core, you'd put a value of 250 millicores. So one thing to keep in mind about CPU requests is that if you put in a value larger than the core count of your biggest node, that pod will never be scheduled because the Kubernetes scheduler will be like, hey, I need this amount for your container to run, and none of the available nodes have this amount available. So basically, it will never be scheduled. So if you have a pod that needs 4 cores, but your Kubernetes cluster only has dual core VMs, your pod will never be scheduled. So make sure that you understand what the physical infrastructure your Kubernetes cluster is going to be running on if they have the thing that you're requesting for. Another thing to add is that unless your application is specifically designed to take advantage of multiple cores, like if you're doing like a lot of database work or doing very complicated scientific computing, it's usually best in normal circumstances to keep the CPU request at 1 or below, or 1000 millicores or below. This gives the system more flexibility and reliability to scale horizontally. When we talk about memory resources are defined in bytes. So normally you'd give a megabyte of value for memory, which is pretty much the same thing as a megabyte. But you can give anything from 1 byte to multiple petabytes of memory resources to a particular container. Just like a CPU, if you put in a memory request that is larger than the amount of memory available for a particular node, the pod will never be scheduled. So let's go back to the pod spec file. So each container on the pod can set its own requests and limits, like I said before, and these are all additive. So if we add up the requests for all of the containers in this particular pod, we can say that 200 millicores of CPU and 150 megabytes of memory is the entire pod's resource request. And the entire pod's resource limit would be the same thing, where we add all of the memory limits and CPU limits all together for the particular pod. And let me tell you why setting limits, setting requests are really important. So when Kubernetes gets a request to be like, hey, I want to deploy this particular pod full of containers to the cloud, Kubernetes is like, okay, where should I put this particular pod? So they scan through all of the nodes to make sure that they're able to accommodate that particular pod. So it takes into account many variables, including resource requests, to make sure that the pod is going to run correctly in the particular environment. So for example, the Kubernetes scheduler would ask, hey, does this particular node have the memory and the CPU this pod needs to run correctly. And if the answer is no for all of the particular available nodes, then that particular pod will never get scheduled. This is why it's very important to set limits and requests correctly with your infrastructure environment in mind. Because you never want to be stuck in a situation where pods are not able to be scheduled, not because there's not enough resources, but because you estimated the amount of CPU or memory needed to run this particular container. So what happens if you don't specify a particular request for a container for memory or CPU? So if no request is specified, here's what can happen. So because the Kubernetes scheduler doesn't have a minimum amount of memory or CPU that is needed to run your pod, they will place it in any available node, which means that let's say a particular node has already multiple pods with multiple containers running in it that is taking up 95% of the available resources. Your pod, even if it needs 10, 15% of the entire node's resources, it'll only be able to access the remaining amount, which means that your particular pod will probably die or not run correctly. So this is why this is really important to specify requests for all of your pods. So requests, like I said before, are for planning. So this is how the Kubernetes scheduler determines where to put your particular pod and container into a particular node. Like it's for planning and putting things where they belong. Limits are for enforcing. So let me get into what limits do. So limits are hard limits for your container to take up specific amounts of memory and CPU. So let's say, for example, I put a limit of 500 megabytes of memory and 1,000 millicores for CPU. If the particular container goes above that limit, the Kubernetes cluster will do different things to make sure that it goes back down into the allocated available amount of resources. So let me show you what happens if you go over the CPU limit. So when it comes to exceeding CPU limits, things get pretty interesting. So CPU is considered a compressible resource, which means that if your app starts hitting the particular defined CPU limits, Kubernetes starts to do something called throttling. So that means that the CPU that is given to this particular container will be artificially restricted by Kubernetes, which means that your app won't be evicted or terminated. Instead, it will just have less access to CPU like resources, which means that it will be restricted. So you can probably see degraded performance from your particular container. So you can, this is like how hitting CPU limits works. However, what happens if you hit a memory limit? So unlike CPU resources, memory cannot be compressed, which means that there's no way to throttle memory usage. So if a container goes past its memory limit, it will just be terminated. So if a pod is managed by a deployment or a stateful set or a daemon set or some other type of controller, then the controller will spin up another replacement for that particular container or pod. But memory limits, when you exceed them, have a much more drastic effect in your environment. So you want to make sure that you set your memory limits correctly and in line with what your environment and your application needs. Another thing that happens when you don't set memory limits is out of memory issues. So out of memory, let's say, for example, you have a particular pod running an application with a memory leak. If you don't have memory limits in place, it's going to take up all of the available memory in the node, and then it will then cause the node to go down, affecting the stability of the entire cluster. However, if you set up memory limits on particular containers, you can prevent memory leaks within a container from infecting the entire node. So it's kind of setting up guide rails for your applications and your containers to make sure that they don't take down the entire application or your environment with them when they have things like out of memory issues. So how about setting guide rails for your entire cluster, not just the container? So the world is a scary and very dangerous place, especially when it comes to the cloud. And people are human. So teams sometimes forget to set limits and requests. And I talked about in the previous slides that if you don't specify a request or limits for CPU or memory, you're basically saying you don't care how much CPU time the process running in your container is allotted. So in the worst case, a particular container that you might be pushing into production may not get any CPU resources at all from the particular node when there's heavy demand by other containers that exist for the particular node. So this might be fine for low priority or non-critical workloads, but if you have critical workloads running in your Kubernetes environment, this obviously isn't the best case scenario. Or you could have a scenario where a rogue team can set up the requests and limits very, very high for their own pods and for their own containers and take up their more than their fair share of the cluster. So there are two things that you can do within Kubernetes to set up guide rails at the namespace level. So they are resource quotas and limit ranges. And I'll talk to you a little bit more about them. So resource quotas are very powerful, and you can use it to restrict CPU and memory resource usage at the namespace level. So if you see on the right, that's an example of how you define a resource quota in Kubernetes. And each section within the spec under hard is optional. So you can kind of mix and match what you want to enforce in your environment. So the request CPU is the maximum combined CPU requests in millicores for all of the containers in the namespace that can be requested. So in the above example here, like in this example, you can see that for 400 millicores of CPU requests, you can basically split that up any way you want. But basically, you can't go over that in your entire particular namespace. So if you have a namespace called development, all of the requests for CPU from all of the pods that are being defined under this namespace needs to have a request value of less than 400 millicores. Request memory is the same thing, but for memory, for CPU. Limit CPU basically is the same thing for request CPU, but for the limit, and et cetera, et cetera. So there are common examples of how you can use resource quotas to enforce like how people consume resources in your environment. So let's say you have a cluster with a capacity of 32 gigabytes of RAM and 16 cores. You can basically allocate particular parts of this particular environment and hardware for a particular team. So you can let team A use 20 gigabytes and 10 cores, and let team B use 10 gigabytes and 4 cores. And then you can hold the rest for future allocation. You're able to do this so certain teams are not getting starved for resources, and everyone is able to go on with their lives and then have proper access to the resources they need for their applications to run properly in production. You can also do things like if you have the same Kubernetes cluster for deploying both your test and your production environments, you can limit the test environment to using smaller subset of the resources like 1 core and 1 gigabyte of RAM, and let the production namespace use any amount that it needs to run successfully. So these are examples of how you can leverage resource quotas to really control the amount of resources that your teams and your developers are consuming in the cloud. But life can be hard. So even if resource quotas can enforce limits for an entire namespace, you could have a team sharing a particular namespace. So you could have a greedy team that sets up very high limits and requests for their particular pod and the containers that are running in it. And then you're only left with the rest of the available space that is defined by the resource quota that the greedy team is not taking up. So how do we avoid a situation like this where people still don't have the resources they need to run their application successfully in production? So you can use something called limit ranges. So unlike a resource quota, which looks at the namespace as a whole, limit ranges applies to individual containers that are being run inside of nodes and pods. So this can prevent people from creating super tiny or super large containers inside a namespace. So if you look at the example on the right, you can see a bunch of parameters that you can set. So let me first start with a maximum section. So the maximum section will set up the maximum limits that a particular container and a pod can set. So the default section cannot be higher than the particular value, than this maximum value. Likewise, a limit set on a container cannot be higher than the maximum value that you set on a limit range. It's really important to note that if this value is set and the default section is not, any containers that don't set this particular maximum value themselves will get assigned these maximum values as their thing. So if you have teams that forget to set limits and limits and requests for their applications, limit ranges will automatically set those values for them. That's where I go into the default section. So the default section sets up the default limits for a container in the pod. So if you set these values in the limit range, any containers that don't explicitly set the limits and requests for themselves will get assigned these values. And same with the default request. So yeah, that's another guide rail that you can set up in your system to make sure that your engineers, even if they accidentally forget to set limits and requests for their particular containers, they're able to still have a situation where the worst can be prevented. So how do we configure all of the things we talked about? How do we configure the CPU requests, the CPU limits, the memory requests, and the memory limits? How do we configure these levers? So if you're here, you'll probably know about New Relic. So New Relic is a full stack observability platform that takes in data from your Kubernetes clusters, as well as your applications running in Kubernetes. So here's an example of something you can do with the data you find within New Relic. So let's say, for example, I have 2 microservices in pods running inside a particular node. If I see that the historical CPU utilization for the last couple of weeks has been 40%, and the highest CPU utilization in the last 6 months was 60%, you can probably tell that you're over assigning resources to a particular node or a pod. So what you can do with that information is tweak your configuration settings in your YAML files with this historical data that you get from New Relic. Because experimenting is key. These values, there's no definite answer for what is the correct or most optimal value for your application. You kind of need to experiment to find the right balance between performance and reliability, as well as cost. So what I would recommend you do is look and make small changes to your configuration files and see what happens in production or prod. See what happens in staging or production in New Relic. So you can see like how particular CPU utilizations go down or up based on small changes you make to limits or requests for particular applications that you're running in production. So this is another example of how you can use experimentation to find that optimal balance between performance as well as cost. So during this webinar, I went over a lot of things, but here are some of the takeaways that I want you to get off this webinar with. So it's super easy to overspend on Kubernetes and in the cloud in general, because the cloud has made it really easy to deploy really quickly and spin up things very quickly with a couple lines of code. But what you can do is you can set up guide rails to maximize the return on investment on your cloud spend by reducing waste, by setting container level requests and limits, resource quotas, and limit ranges. And finally, you're able to leverage observability and New Relic to fine-tune these values that we just talked about to get the most optimal configuration that balances performance and reliability with cost. So yeah, that's kind of my presentation. Let me know if you have any questions. And yeah, thank you.
Yeah, we'll hang out just a little bit. If anybody wants to write in the chat, raise your hand, feel free to ask. Otherwise, have a great day.